Okay, thank you, Joe, for the introduction, and good afternoon. I'm Deying. It's an honor to be here at UMD and to talk at this BBL speaker series. And also it's first time to be here at UMD. It's a beautiful campus, and it's nice to walk around here, especially after the snow. Um, so I'm gonna talk briefly about an earlier work. Actually, it happens before WIST 25. It's published on Chi 24, and that will transition to the second work, which is the last year's WIST. So something about me. So I'm always interested in how we use computers to make things like you see here. Sorry, why is it not? It's not playing, right? This video, but it's fine. I'm always interested in tangible stuff and fabrication. So my work in HCI centers around digital fabrication and computational design. My main goal here is to provide tools that push the boundaries of fabrication techniques and to develop methods for everyone who wants to make their own things. So, in personal fabrication, FDM 3D printing has become the standard of rapid prototyping because it's accessible and cost-effective 3D fabrication technology. In the office, it's usually okay for us to stick with glue sticks and paper clips, so it works well, and especially on papers. But in more high-stakes situations where you're like building bridges in airplanes, you need welding, you need riveting for larger structures. So these methods really evolved over time, over hundreds of years, and they all work very well in their own context. But when we apply them to 3D printing, they really fall short in so many different ways. For example, the adhesive, the glue adhesives on the left, they usually make permanent connections, but they leave glue marks or other cosmetic issues. For touch fasteners, it relies on the adhesive backings, which can fail over repetitive use. And they're not really customizable for commercial products, like if you're using like off-the-shelf products like 3M Command. For mechanical fasteners, we are very familiar with that. It's great for non-permanent connection, but they need extra effort to tighten the screws and of course to connect and disconnect. And they require extra design accommodation in the modeling process. So to tackle this problem, Maker actually pioneered 3D printed touch fasteners. All the way, you can date it back as early as 2011, which is still the early stage of sharing files online. But just like 3M command strips, these designs are typically shared as static, unmodifiable mesh files. So while some parametric tool does exist, they are often limited to generating basic rectangular patches. And current studies in HCI fabrication communities have also inspired our work. Celia, for example, used SLA 3D printing, which is resin printing, to make delicate hair-like structures with adhesive properties. TrustFab provides a method to connect plastic bottles and turn them into large structures. And Shrinkage here proposed a technique for attaching 3D printed parts to existing items for repairing and decorating. So for some of you who have some engineering background, you might recognize this chart. And our idea for this study is really somewhat similar. We want to make a connection method that is as universal as duct tapes, but more importantly, customizable to accommodate both static and dynamic connection. So I'm gonna talk about this work published at Chi 24 briefly. So how does it work? We begin by designing 3D printing and testing different touch fastening microstructures that we call little mushrooms. The binding, in fact, is really the result of compression and friction. So our goal here is to produce various fastening units to provide options for different engagement characteristics. which one of which is the holding strength. As you can imagine, the strength relies heavily on the density of the pattern as well, which we have a name for this density or tolerance. We call it spread ratio, which is basically a multiplier for a default distance in a pattern. So a spread ratio of 1 stands for zero tolerance. This parameter helps us to create different fastening performance, which can be calibrated to reach an optimal value. Depending on the material and the 3D printer you're using, a spread ratio of 1 is not always the best option. So the drawer example here is one scenario where we use a spread ratio to customize the holding strength of the connection. And we also have a tilt unit tilt, which provides non-uniform shear resistance. What do I mean by that? So we control these two angles shown in this diagram, the tilt and direction, so we can customize the fastener to counter certain loads. Like in this example, the anchor hook's upward tilt and the baseboard's downward tilt ensures better weight-bearing performance against gravity. So this third unit here, we call it slot unit, is one of the two ways to enable a dynamic connection. The locked and the sliding modes can be switched in a simple planar rotation. Like in this example, the rotation is 90 degrees between the locked mode and the sliding mode. And here's one example with a slot unit. The locked mode offers a simple fixed net connection as the other units do, while the sliding mode grants a single degree of freedom where the connected objects can perform linear motion. Besides extruded units, we also have taper units, which are the combination of conical frustums and cylinders. And what it does is here's an example where the taper units helps establish a secure connection on an actively changing curved surfaces. This is an elephantoid with a articulated trunk. The taper units are arranged in low density to achieve a loose connection. So compared to static patterns, the dynamic patterns offer the freedom to move things even when they are connected. So the toy car here is one example where we apply the circular pattern to achieve a dynamic connection instead of connected by like traditional assembly like a rod. The four wheels are connected on two matching circular patterns. The patterns are optimized for a higher weight-bearing capacities. Here's another example of circular pattern. When you blow air to this windmill, it starts to rotate and picks up speed instantly, which shows that it has really a low resistance if you do the correct design customization. And last but not least, the gray cloud on this bonsai clip art is an example of linear dynamic patterns, which works basically very similarly to the previous the circular connection. So to recap Touch and Go, we propose this universal and customizable solution for temporarily connecting 3D printed objects together. But I don't know if you already noticed this. There's one limitation. It only works on planar surfaces, which means flat surfaces. It does work like relatively and to a very limited range that our design tool does support curved surfaces, but really the laws of physics tells us that you still need enough area of contact to make a robust connection. So starting from that, I started to look at other connecting methods human has other than touch fasteners, and I found this, which some of you are holding right now, is the zipper. So what can we do with zippers? We went on to develop touch and curl, which was presented at WIS last year. It's a method for creating linear and skeletal structures using an assembly mechanism called similar to a zipper. We're interested in making curved and skeletal structures instead of those boxy straight ones. So curves and skeletal structures can really be found almost everywhere, such as in architecture, art installation, and product engineering. But they're difficult to manufacture, transport, and assemble due to their complexities. When we look at HCI, existing methods have already accommodated various types of geometry, such as wireform, grid shells, and truss. But there are three major challenges. Their fabrication process can be material and time consuming. the assembly often requires excessive labor and involves a steep learning curve, and they often cannot be modified or reused after the final shape is formed. So in contrast, excuse me, we set off to propose a new method that integrates efficient fabrication, easy assembly mechanism inspired by zipper, and to effectively produce a wide range of geometries. So let's talk about how it works in detail. We are very familiar with zipper because it's an interlocking device that connects flexible fabrics together. The zipper's flexibility makes it well suited to conform to dynamic surfaces and flexible surfaces, but it also means that once it's closed, it cannot maintain its shape very well because otherwise it will be very uncomfortable to wear it. Um, to address this, we add a thin ribbon under the zipper teeth to form a pair of zipper chain that can be 3D printed. So next, we apply the curvature and torsion to the previous the straight zippers, and which we get. So on the top, the curving left and right in the horizontal plane. In the middle, twisting clockwise or counterclockwise along its axis, and on the bottom, bending up or down away from the horizontal plane. So by combining these 3 degrees of freedom, we can bend and twist a zipper into any smooth differentiable space curves, given a finite degree of curvature and torsion, like this one showing here. And finally, by connecting the ribbon of multiple zippers, we enable the branching, which is useful to build a skeletal model. So that's basically how the zipper works. The parametric model has given us the tool to control its shape, but it will not be complete without a computational model to perform the inverse design, which actually matters to the users. So our goal here is to develop a pipeline that takes the 3D mesh or skeleton model as the input, construct the 3D ribbons, which will be flattened into 2D ribbon, and then generates the final zipper assembly. So this process begins with mesh partitioning, a necessary step before flattening a closed mesh or any model that exceeds the 3D printing platform size. So it's also critical to maintain the connectivity between partitions for structural integrity. So for example, if this soccer ball doesn't fall apart on its over its equator. So next, we performed tree rectification to make sure the vertex is flat instead of pointy. To do that, we find the rectification plane on every vertex based on the tangents of each branch and rotate the branches accordingly. We also update the branch to compensate the relative movement between the vertex to make sure this adjustment only affects the model locally instead of significantly changing the input form. So from that, we construct a ribbon based on the process mesh or the skeleton partitions using some like crazy weird math. Every curve branch can be discretized into arcs that are tangents to their neighbors. By offsetting these arcs, we can get a collection of smooth conical surfaces. So what's good about conical surfaces is that it has zero Gaussian curvature everywhere, so it's developable by nature. Therefore, we can flatten the process can perform the flattening by conducting through this isometric mapping, which unrolls the 3D ribbon into 2D. With that, we can parametrically generate the zipper assembly that is ready for 3D printing. So as shown here, this simple yet robust computational methods enables us to accommodate a wide range of model across different levels of detail, overall scales, and skeletal complexity. Sorry. So let's quickly go through the workflow of touch and curl. The user stuff from importing the model into our design tool and then setting the basic parameters. Our pipeline would automatically generate the partition and process the model and produce the zipper assembly that is ready for 3D printing. So after that, the user will manually assemble the model, which takes between a few minutes to, if you're doing something like larger or like a more complex, it can be like 20 or 30 minutes. And the final shape can be formed, which you can see here. The mechanical rigidity of the zipper is tunable. It you can do something as flexible as this flower vase, or it can be a continuous, like a rigid loop structure to achieve additional functions such as lighting, which we embed a really like a simple LED strips into this between these zipper structures. So, in conclusion, we have developed a technique that combines efficient manufacturing with a zipper-like assembly mechanism to produce a wide, diverse range of curved and skeletal forms. And although there's still a long way to go, we would like to imagine both studies being used in different scenarios to help people's lives. So, for example, this connecting method of touch and go will facilitate a more modular design in products made by 3D printing, which is really a new thing, but it's growing rapidly. So instead of replacing the whole item, you can swap out one of the few parts to reduce the material waste. For touch and curl, we imagine our zipper can be used in situations that can benefit from small package footprint that can be deployed on site with easy assembly, such as this emergency shelter in extreme weather condition, if we can figure out how to 3D print stuff that's this large. Well, it does exist. Not like thermoplastic. We already have like a concrete 3D printing, but that's another topic. So if you have access to 3D printing or just want to take a look at our design tool, you can scan these QR codes to download the sample model at the GitHub repo. But like I said, it's great to talk about these works. And if you have question, I can take answers. I'll take a question from right here. But I also have some free samples to give it to you.